Hello, good afternoon, everyone. I hope everyone is doing just fine. I'm sorry I couldn't be with you last Tuesday. I had a family member. It's my child. I hate to say that my child is sick. I don't like to say it even. He was feeling unwell, so I had to stay with him at home. So, what did we do last time? So this module is a very easy peasy, simple and soft. I feel like it is very light, rather. So it is talking about how we predict future sales for technology, pharmaceutical, any innovative or new products in the market. So this kind of products, research and theory unless your product in particular, if you have innovated some product, unless your product is not a very successful product, it will not follow the S curve. But if your product is going toward success, then basically what's going to happen is it's going to show an S curve for its growing sales or market share. So we're talking here about the expected cumulative values. So the total number of people altogether, the total number of sales altogether over time. So usually the expected value is plotted on the y-axis, and on the x-axis you have time. I also took my time to explain in depth how did we get with this S-curve and why is it a theory? And how is this theory related to so many other models in management and marketing? And one of the models was the model for adoption of innovation model. So adoption of innovation model is particularly is what we're talking about when we are selling a newly innovated product and we want to predict the total sales. So as you can see in this graph, in this figure, of course, we have the innovators like ourselves, very creative people. Of course, they're going to adapt to new ideas easily. Early adapters, from their name, they are rich people who like technology. They are not innovators like ourselves, but they could be our investors, the people who are very much into technology and open-minded to trying and adopting new technology. Then there is the early majority. This is where the money is. This is the mainstream. From this early majority and late majority, this is what we call it the mainstream. It has covered the whole market, and the increase will be humongous here. So this is a growth also phase of your sales. So if you're looking at the product life cycle, that would be the belly of the growth rate. And then over here, if you can see this model, it looks like a normal distribution because it's talking about human beings in the population. And this is if the population is normally distributed, and most of the populations, as you took in statistics, over 30 as a sample size for continuous data, you could probably pass the assumption of normality if it was withdrawn, this sample, from a normally distributed. And it was in statistics found out that most of populations are normally distributed. So with the normal distribution, you all know that this center is the mean. So over here, as you can see, this also overlaps in ideal situations, ideal normal curve, ideal S curve, which an ideal S curve is this part over here is totally completely in the center. So this is like a 50% over here, this inflection point. So the inflection point will be overlapping on the mean, the peak of the normal distribution. Then that doesn't mean that we are going to, the sales will disappear. It just will slow down. But this is the cumulative sales. Some of you will say, come on, I see it growing. Yeah, of course it will be growing. But the rate of growth, the increase rate is less. For example, when I was a bébé, when we took a regression analysis, when we were talking about little infants, they grow too high, they grow too much. And when they are kids, you were growing too much. And then you were still growing when you were a teenager, but the growth rate has slowed down, but you're still growing, right, guys? Until we absolutely had stopped growing and, well, started aging. No, actually, you stopped growing, but then you were all beautiful with the glowing skin and all that. I'm telling you, until 30, I was all right until 35. So hopefully you will still also be all right until 35. Just eat healthy, don't smoke, don't drink too much alcohol. Then things go downhill from that. In any case, I want you to understand this as your growth and aging process. You don't immediately fall. Don't immediately start aging, right? You live some little 10, 20, 15, 10, 15 years before you actually head down south and start sagging. Anyway, so I hope you are now, I hope you now understand how this curve is very important, and I'm very happy that we had some time to discuss this curve before the end of the semester and how it is relevant to so many marketing models. All right, I talked about this, so no need. And then I told you I wanted to convince you that this is not blah, 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 blah. This is actually true scientific statistics. So I am showing you that, I'm reminding you that the cumulative normal distribution, this is the cumulative normal distribution, guys, and you took it in statistics, right, lovely people? So if you cumulatively add up all these together, so when we add small slices together, this is like what? This is integral, isn't it? When you took it in high school, that these little slices you add, first of all, you segment them in the little slices, 1 units usually, and then you add them up together. And what do you get? You get that area under the curve. And when you're getting the area under the curve, basically this is what we call it what? Cumulative normal distribution. All right. So we had demonstrated here the use of this formula, this equation with Excel, and I showed you how to use it last time. Now let's jump to next time, or this time. Welcome to fitting the pearl or logistic curve. What is logistic curve? All right, let me take some time to show you what the logistic curve is. Lovely people, we took regression analysis, right? And with regression analysis, what happened is we had y. Oh, what happened? What happened is I haven't hit this little button. So what happened is we were talking about y and we were talking about x, x1 all the way to xn. Gosh. Anyway, this y was continuous, was the number of sales, for example, of rice balls, right? So the type of the data was continuous. With logistic regression, we use logistic regression when the type of the y, the type of the data of the y is binary, is discrete. So what do you mean by binary? It's like a category. It's either 1 or 0. So we define it as it's equal to 1 when you belong to that class, to that group, and 0 otherwise. So that was the standard definition. You say otherwise, 0 otherwise, 0 otherwise in your thesis or wherever you're writing. So we always say y is equal, if you want the truth, we say y is equal to 1 when it is belonging to the class, or when it's greater than or equal to a certain threshold, and 0 we write here otherwise. This is how we write it, okay? In any case, this is the difference between linear regression and logistic regression. Logistic regression, y is binary. Y is 1 or 0. Y, linear regression, is basically linear. All right, so there is a scientist called Reed Pearl. Pearl talked about the model the path of the product diffusion or penetration. So product diffusion. Why do we say diffusion? Because we're talking about technology innovation, and probably you've heard of the diffusion of innovation, right? Diffusion of innovation. So Reed Pearl has talked about this product diffusion. So he's a demographer. And his Raymond. I'm sorry, not Reed. His name is Raymond. I messed up with another scientist. I'm really sorry. his name is not Reed, his name is Raymond. I'm sorry. So the Mr. Pearl has found out that we can fit it on the logistic curve. So let's take this x of t. What is x of t? It's a function of time, because we always say here on the x-axis we have t. This x over here is not the x-axis per se, all right? So x of t, all right, the function of time, is equal to some L, and this L is cumulative. It's a cumulative sales by time t. So what is x of t? It's the per capita at time t. What is per capita? Number of sales per capita, sales per person. So here we are trying to find out the sales per person. So we are reversing the situation here. So we tried the sales per person per head per capita time t. Here's what happens when my son falls sick. I just hug him a lot and all that, and to soothe him, and then I fall sick. Then we have L as a cumulative sales by time t, or L could also be the percentage of the population. Remember last time we were talking also about the percentage of the population, and what is the percentage also? We say percentage of market share. So percentage of market share. So always think of it this way. So how do we find this sales per capita over here, xt? It's easy. We need to find L, and there is A. This is exponent, so exponent is already found, and there is P. Actually, it is E to T over B, and this is equivalent to E minus B T. So if you're thinking why is it minus, it's not minus because the parameter per se is minus, it is T over a certain time, because we're talking about here a percentage population, right? Or cumulative sales. Over here T is over B, so it does make sense, right? So minus BT. I want you to understand why it is minus. So minus BT, and there's A. A could be 1. If it's 1, it will be E minus BT. But sometimes we need to, this A is there to show us how the curve, where the curve shifting on the x-axis. Is it here? Is it here? Is it here? So the higher the A, the more the shifting in the positive. Let me show you. Let me show you. So let me show you, lovely people. So we have A. A could be 1. 1 times E to the power of minus 1 times, let's give them all 1. 1 times T, let's T have it to be 1 also. It will be this value. So let's put it as A E to the power of minus B T. Add a slider. So let's say that A here is this value, B here is this value, T here is this value, and you can see how the values, it changes. So over here, let me put L over 1 plus this. It should be able to plot it, but let's put here X instead. See what happens. Yeah, let's put this X. And these are parameters. Okay, so now we can find out how A changes Do you see? Actually, A over here, I thought that this is totally linear here, because with logistic regression, we are trying, this is the probability or the sales per capita. So the output of logistic regression is actually probabilities. And then you need a threshold so that you can say anything above is 1 and anything below is 0. So the way that we fit logistic regression is is like the general regression, like linear regression. So if you're taking a look at A, for example, over here, that the A and B here, as you can see, here's B is the one that's shifting. Sorry. So B is the one that is shifting the direction. So when B is here, it's in the positive. We're actually, B is always in the negative. So this means that over here, the small number, even the smaller values will be shifting the direction. And of course, T will also shift it like P. All right. So when A is not in the negative, A is always in the positive. So A is usually in the positive. So you can see that A is also shifting. So I don't know why it wasn't shifting that much. So A is also shifting. So now it is all right what I said earlier. So A is shifting the curve, either higher or lower increase rate. The same applies to P. P is in the other direction. So do you see the the situation? This shifting it a little bit into this direction, a little bit counterclockwise. This is more of also counterclockwise, or actually clockwise. If you're going this, the more increase you're going this direction, it's clockwise. This, as you are going higher, it's also going clockwise nonetheless, as it's going higher. And of course, this is the T. T is usually positive and increasing. So you can see that the calibration here isn't easy. What are the values of L, A, B? T, we can understand the values. The values are increasing 1 unit on the x-axis. So this is actually the T. Maybe this is maybe the Y indeed. Actually, this is not the Y, because no, it's an L, just an L. For one reason, the Y is this value, and this is the T is on the x-axis, and this is just an L, and this is the cumulative values of the sales. All right, so this is very complicated for us to solve, right? So we need to use solver. So I just wanted to show you this demonstration so that you can understand the complexity that we have 1, 2, 3 parameters, 3 different parameters that kind of, if you just exchange one of them for the x, you will see how each parameter, as this increases, this increases. As this increases also, this increases. Yeah, you can see that, or decreases actually, because it's in that denominator. And this, as it is increasing here, it is also decreasing. You see it's 10 to the power of minus 12. Please notice that. So these, because they are in the denominator, A and B, they are actually going toward decreasing the values, while L over here, as it is, you can see as it's increasing, the value also increases. All right, good. This is very important because the next step I'm going to talk about certain properties. So as you can see, we're going to use the GRG solver so that we can find the values of L, A, B and the best equation fit. But we need to note that when T grows large, the term AE minus BT approaches 0. Did you notice this when we were doing that the curve itself, when we put, for example, T to be, I can't see very well here, when we put T to be X, for example, and over here we put it to be X. So this is the S curve that we're talking about, because this is the real X. I just wanted to show you the behavior of L nonetheless. This is why I put it as x, but actually the x is the t. So this is looking like an S-curve, but it is a little bit, this is A in positive, this is B in negative. Ah, wait a minute, I already put minus here. If I didn't put minus, then I should put B here, I'm sorry. So this is the idea. So B here is positive because here I already put the negative. So this is now an S-curve. All right, so now that you can see, when we put t as an x, which is the x because it's plotted on the x-axis, now we can see that as L, as you can see here, what are we talking about? As L increases, not L, as the t grows large, the term, this term alone approaches 0. Okay, so this is x. As x increases so much, this value will be approaching 0. So you can see here x is 0, and then when x increases, if you want, you need to take a look here at this value only. So let's just take a look at this value over here. So this one we want to see. So as x increases, do you see how x here is the highest? Look, this is x at the lowest. So if you see x here is high, this is the term ae minus bx, the one in green. Do you see the one in green? As x increases, you can see how it is approaching 0. Here it is 0, right? It's too much of a 0. So basically, this is an S-curve, and this is what happens when x increases. So as x increases, this value, which is this term, ae minus bx, is approaching 0. This is what we mean by that, okay? So if you're plotting this term alone, this one alone, in the green, you go higher. So this is part of the the S-curve. Then 1 unit increase will yield to that this term is approaching 0. So you can see that it is actually laying down on the 0. Okay, where are we here? And let's talk about, this implies the following. If you model cumulative sales, then the cumulative sales per capita approaches what? Let's take a look. If this value will approach 0, like this formula here, will approach, these guys here will approach 0. This will be 1 plus 0. And L over 1 plus 0 will be L over 1. So when this approaches 0, when T is too high, then this sales per capita will approach the value of cumulative sales by time T. So the cumulative sales per capita approaches the upper limit of L. If you model actual sales per capita, then actual sales per capita approaches L. If you model percentage of population to have tried a product, then the final percentage of people to have tried the product will also approach L. Good, good, good. Now, together, A, B determines the slope of the S-curve. I showed you how. Of course, I had to manipulate a little bit and put X to be L rather than X to be T, so that I can show you how this so. Because over here, this is what I needed to show really. So over here, let's see how A, this is what I told you earlier. A will shift the curve up and right and left. Do you see? So as A increases, the curve a little bit, the slope, it changes. So it is a little bit more leaning to the and shifting to the right. Do you see that? However, over here, the same happens. It's a little bit shifting, but up and down. Do you see that? Do you see, guys, the difference in the slope, how they are actually determining the slope? So these are very important then. When you are putting L over 1 plus e to the power of something, which is x, this is how it's supposed to be, right? It is supposed to be here, L over 1 plus e to the power of x. Right, guys? to the power of x. So originally it was looking something like this. Do you see it? Do you see it? But this is not the S-curve that we're talking about. Let me silence this one. This is originally, it was looking like this without parameters. If you're questioning yourself, why do I need A and B? Do you see this is without A and B, but actually the S-curve is the inflection, the inverse of this. So we need here a B. So actually it is, if we put a B here, nothing happens. For the x, for the t here. If we put a b, nothing happens. But if we put minus b, which is x over b, then you can see how we kind of inverted the situation. And also, this way, when b changes, as you can see, the slope changes, but if it changes maybe too fast and too sharp. So we need maybe a, so that we can also take into consideration the up and down. Do you see here? Now this is L, sorry. Do you see here the right and left? The A shifts always right and left, shifting a little bit here, right and left. And the B, as you can see, is a little bit more severe. So we need these A and B so that we can precisely capture, or we can precisely configure the curve. So the S-curve can precisely now be configured as a slope here. You see? You see that? The A is mostly shifting. Do you see? The curve stays the same. It's just shifting its movement on the x-axis. But the B really is the one that shifts the slope. So if you want the truth, the way that they probably started with this curve, it was L over 1 plus e to the power of bx, or x over b, or minus b times x. But then, with some research, they needed to shift it. So also mathematically, you also need to consider the position, relative position to the horizontal relative position, and this is more about the slope. I hope that this demonstration, even though it took quite a while, I hope that it helped you understand the importance of A and minus B, because this is always a problem with the students. So first, I showed you the importance of L. L, if we put it as an X now, I showed you how it is relevant in terms of its direction to. Actually, L doesn't really change, it's the same line. What it changes it and makes it goes counterclockwise or clockwise is the A's and B. So this is also a demonstration of the importance of A and B. However, please be guided that the X is actually the T. So this is where you started seeing that S-curve. And then I wanted to convince you here that the curve originally was only L over 1 plus e to the power of t, which is the power of x power t, and it was totally completely in the opposite, mirrored. It's like you're seeing yourself on the mirror. It's the inverted, yeah. It's not. It's inverted. So what we needed to put this x, as you can see, here's the x. We needed to straighten this up by putting x over b. So do you see x over b here? So with this is still not really the optimal situation, x over b. So we needed something like minus b. Yeah, do you see the difference? Minus b, and then here x over b is still not the solution. You're looking at this whole thing over b, also it's not a solution. So do you see what I'm trying to tell you? Why minus b? So over here we have minus b. Okay, minus bx, a e minus bx. And now hopefully you understand the importance of A. A is just shifting this curve, and B also more effect on the slope. I'll see you in the next video, and in the next video we are going to work on the Excel sheet. What is it called, the Excel sheet? It is the world cell. So we're going to talk about the inflection point, which is equal to the logarithm. Why logarithm? Because we have exponent. When you have exponent and you want to find, it's very much related to the logarithm. There's relationship between the natural logarithm and the exponent. So we're going to talk about it maybe next video. So this video is getting very long. So this is the inflection point is a logarithm of A over B. So we're going to talk about the world cell Pearl Excel sheet in the next video. That's a bit long, this video.